Welcome back, everyone. There are 6 other people in this lecture. Oh, wow, the midterm certainly did a number. But, okay, so we're not discussing the midterm right now. There's a 24-hour moratorium on discussing the midterm, but we'll do a postmortem on Thursday. Again, the midterm does not have a denominator, and it is going to be heavily curved. Looking at the scores right now, it's trimodal, as I predicted, with, I think, the second mode being less than 50% of the maximum number of points available. So don't worry about your performance now that the midterm is over, but hopefully it should have been a very good indicator of what it is that you need to study. And also fun for some definitions of fun. Now, non-midterm questions. Does anyone have any material questions?
Yes, I do. Just looking at the rules that we've been discussing last lecture, the 3 rules of natural deduction. So can you explain, I understand, we have a proof tree that we're building bottom up, and then we can explain a proof going from top to bottom. Is that correct so far? The question is, so, but then my question is, can you clarify context? So what does it mean when something is in a context? So does that mean this is something that's already, we have proofs in there, something that we already know that we can use?
Well, it's not something that we've already proven. It's something that we can use. Now, this idea of you construct a proof tree from the bottom up and you read it from the top down, that's a helpful analogy. But proof trees also, one way to think about them is that they're just mathematical objects on their own right. There isn't a necessary way in which you have to read them from top to bottom or bottom to top. They exist. They're static in time. And you can build proof trees using the inference rules. If you're actually thinking about how to build proof trees from the ground up, then you're building them from the top to the bottom. That's how you build proof trees. And that's why it's somewhat natural to read them from the top to the bottom, because that represents the process of actually constructing the tree. Because in order for a sequence to be valid, that means that it is the conclusion of some valid proof tree. Is that right? Right?
Yes.
Do you understand that point?
Yes.
So then the question is, if a proof tree is supposed to convince you that the conclusion is a valid conclusion, that's the point of proofs in order to establish something. Then the proof tree does that by showing you that the conclusion at the bottom of the tree is indeed a conclusion at the bottom of a valid proof tree that has been constructed by applications of the rules from nothing. And that's why you construct it from top to bottom. When you're actually trying to work out what it is, you can work backwards from the answer to try and discover how you get to the answer from no assumptions. But the actual proof is a construction of its conclusion from no assumptions. Now, when I say assumptions, I don't mean contexts. I mean assumptions that some sequence is valid. So I think one good starting example is consider this. Consider the sequence. So here I'm annotating it with proof terms. Is this sequence valid?
I don't know at this point. Well, it depends. Okay, it says, well, I don't have anything on the left side of the turnstile, but on the right-hand side of the turnstile, it says X is a proof of A, and I could say that's an assumption.
the question is that a valid sequence? In other words, can you construct a proof tree with that as its valid conclusion?
Not sure, but could I say A implies A, or not even?
Well, so the thing is that I showed you last class the Proust code for type checking and type inference. Sorry, for type checking and type synthesis. That was about those two functions together were no more than 15 lines of code. And those 15 lines of code are able to verify valid sequence. So there's a purely mechanical process for determining whether or not this is a valid sequence. What is that process?
Okay, so there was type checking and type synthesis. Are you talking about?
Yes, so let's suppose we try and type check X against A.
Well, for type checking, it said that we need to succeed in constructing a proof tree.
Yes, the program is attempting to do this. Let's say the program is attempting to type check X against A in the empty context. What does it do?
In empty.
Do you have the rules written down in front of you?
Yes, I'm looking at it. Okay, so given A, I need to check or verify X.
So how do you know which rule had to have been applied as its last thing? So the question is there a proof tree if this is its valid conclusion, right? Well, there's only a single rule that could have applied. Okay, right. So first off, that rule is the variable rule, right? But that rule operates in synthesis mode. So the first thing that happens is that the program changes to synthesis mode. And it tries to synthesize the type of X in an empty context. And then what happens? Which lambda calculus variant is X? This isn't something that you should look up. Off the top of your head, which lambda calculus variant is X?
Just variable.
Yes. So which rule applies to variables?
So the variable rule is the one
Yes.
that says, yeah.
And what computationally does the variables rule do? How do you synthesize the type of a variable?
It puts the X in the context.
No, it doesn't.
No, it doesn't.
That's what implication introduction does.
Okay.
Okay, so the problem is this. You're working in an empty context. You have X, and I've asked you to synthesize its type. What type is X? What is the unique type that X has?
Well, it should be A. There's nothing else.
Oh, what about B? Why doesn't it synthesize B? Remember, this is the only problem that we're trying to solve. Nothing else in the universe matters. It's only this. You can forget about everything that happened before. Why shouldn't the answer be B? So there's no way to answer this question. Why should X type check to anything? You have no information that tells you anything about X. What the rule actually does for the variable rule is that it looks X up in the context. So it tries to see, is there something in the context? And the context is blank. So this fails. So synthesis fails, so type checking fails. So this is not a valid sequence. On the other hand, if you had the following sequence in context X, in the context where X is known to have type A, synthesize the type of X, then what do you get?
Well, it can look up X, right? It's in
Yes.
the context, yes.
Yes.
Then it goes to A,
Yes.
implies A.
No, that's not an implication.
No.
There's no
It's
implies.
not.
This isn't implies. This is the symbol for type synthesis.
Okay. So how would you read it then?
So that's the purpose of contexts. Contexts
Okay.
store information that you know. And the other motivation is think about hypothetical. If you're trying to prove A implies B, you assume A and you prove B, right? How
Yes.
do you, well, you need to keep track of your assumptions. So your context keeps track of your assumptions.
So in the end, what should be in the context? Like all the proofs, all the proof terms, or what?
Well, no. So you start with some sequent, right? Gamma, T colon T, and you're trying to verify the sequent, right? And then the rules tell you how the context changes. So for example, typically we'd like to prove results that hold with no assumptions. So typically we try and prove something like in the empty context, let's say lambda x dot x is a proof of A implies A. So this is a valid sequence. Right now the context is empty. And okay, fine, let's do this example. So type checking and type synthesis are algorithmic problems. And the algorithmic problem that they solve is the validity of a sequence. Let's say we actually change just the statement that this is a valid sequence into an algorithmic type checking problem, right? Okay, tell me how what rules are followed. What rule applies here?
The implication introduction.
Okay, and what does implication introduction, the rule say? So what sequence am I verifying here?
So
Don't look things up, think. The rule for implication introduction, I'll write it down. In context gamma, lambda x dot x. Let's say I'll write it as a bidirectional rule. This type checks to, sorry, lambda x t. Type checks to t implies w. provided that in the context gamma, with the additional assumption that X has type T, that T type checks to W. Okay, so how does this rule apply here? Tell me what sequent I write here.
In the context of gamma.
Nope, there's no
X,
gamma. What gamma? What does gamma mean?
The context.
Which context?
The context.
What is the context in the bottom line?
Nothing.
Yes, the empty context, but there's no gamma. Gamma is meaningless. Gamma is a metavariable for context in this rule. You're not writing a metavariable right here. You're writing an actual sequence. So what is the context in the top line?
X is a proof for A.
Yes. And in that context, what are we trying to do?
That A type checks to X.
A doesn't type check to anything. A is a type. Types don't check to things. Terms type check to types.
Terms, okay. Well, it has to be X as the.
Yes, X is a term. So X type checks to what?
A.
Yes. So that's, okay. We were trying to verify this. Now we're trying to verify this, right? How do we do that? Algorithmically, what happens next? Look at what we did before here.
Yeah.
Could I please get an answer?
Not sure.
Okay,
So,
what happened here? Explain.
not sure.
Okay, well, I'll tell you what you should do is you should read the notes. What happens is you apply the turn rule in order to switch from checking mode into synthesis mode, and then you try to synthesize the type of X in a context, in that context. Then in that context, you look up X in the context. Let's say the context where you have X is annotated to A, and this lookup succeeds. You get A. So since the lookup succeeds, the synthesis succeeds, then you check that that's what the synthesis produced is the same thing that you were trying to type check. So this premises of the turn rule are satisfied. So this type checking succeeds. And so the original type checking succeeds.
Okay.
And this just follows the rules. You don't need to think above the wrist when doing this. You look at what this is and you say, well, I'm trying to type check a lambda. What rule applies to type checking lambdas? There's only one. Here, I'm trying to type check a variable. There's no rules for type checking variables, but the turn rule lets you switch from checking to synthesis. And when no other rule applies and you're checking, you switch to synthesis. Okay, trying to synthesize the type of a variable. What do? You look it up in the context. The context lookup succeeds, then it goes through to the bottom.
Okay.
Any other questions? Okay, now I'd like to ask a question, which I'm sure some of you have solved or you have read the notes and already know. When do the bidirectional type checking rules fail to verify a sequence that has a proof tree? So in other words, if are there any sequence, valid sequence, gamma in context gamma t has type t, for which gamma t, if we try and type check t in that context, this will fail. What do people think about this? Anyone? What about a guess?
I would think no.
That seems very likely, and also one meta reason to think not is you'd hope that we'd write rules for which this doesn't happen. But consider the following case. Suppose, well, we know that in the empty context, we know that in the empty context, lambda x dot x type has type t. Sorry, A implies A. That works. Now, consider the following thing. Consider lambda xx applied to lambda xx. And I claim that this has type A implies A as well. And let's try and construct a valid proof tree from this using the monodirectional rules. So how would I do that? So I'm not using bidirectional rules right now. I'm just trying to construct a proof tree that has these colons. But you can still know which rule was applied at each step because you still have proof terms. So what rule had to be applied at this step?
Don't applications usually mean it's implication elimination?
Yep. And so in the same context, right, does implication elimination change context? Does it?
No. No. Sorry,
Okay.
Come on.
What am I trying to do then? What do I need to do?
You got the first in the application, the F, which is the lambda XX colon A. Okay. And then you got.
Is that
Oh,
right?
no, sorry. It got. Well, it says T implies A implies A.
Yes. So something. Let's leave it as this. A implies A. Right. And then the second item is that in this context, what?
Yeah, you got the second application, which is the same thing, lambda XX.
I don't hear you.
Lambda XX colon
Mhm.
the something we don't know.
Yeah. Now, let's try and fill in the somethings. Let's try and fill in the something from the second term. What's a reasonable way to, so first off, a lambda XX has type T to T for any T, right?
Yeah.
So it'll type check. You can construct a proof tree in which it's a valid conclusion if you replace T with any type. It'll type check to any arrow where the left-hand side is the same as the right-hand side, right?
Yeah.
Now look at this. We're trying to show that this has the type of some arrow type, right?
Yeah, something to the same something because it's the
Hand side B. Sorry, I don't hear that.
So it's like we're trying to determine the type is something to the same something.
Yes, so what should that something be?
A implies A.
Yes.
Oh.
And then that's what goes here as well, right?
Yes, that's lovely.
And then for both of these, we can these proof trees because the identity function type checks to anything, it goes to anything. So how do we do that?
Introduction, because lambdas.
Right, so here X is assumed to have type A implies A. And then we're trying to do what? Determine whether X has type A to A. And here we're assuming that X has A, and we're trying to show that X has type A, and both of these work by the variable rule.
Yeah, and they're also contradicting.
But notice that by our rules, we would have to synthesize the type of this lambda. And there are no rules for synthesizing types of lambdas. So trying to synthesize, trying to type check this term will fail. Now, if you actually think about it, what does this say in the world of functions? So lambda xx is the identity function. I can do it like this. That it's the identity function says that if we give it a computational meaning in which substitution actually happens, if you give it anything, what does it return?
Returns the same thing you inputted.
Right. And so if you give the identity function something of type A, it'll also return something of type A, right?
Yes.
And if you give the identity function, which has type A to A, it'll also return the identity function which has type A to A.
Yes.
So that suggests that actually here, this is an application in which the first thing is a lambda. And perhaps if we perform computation, then this term reduces to lambda x dot x, and that is a proof that we can type check for A to A. So computation, we said at the beginning of the course that perhaps we should consider all things which are related by computation to be equal. 2 implies 2 equals 4. You've performed a computation there, right?
Yeah.
And here you've applied the identity function to the identity function and gotten the identity function. So that application should be equal to the identity function. And in particular, those two things should have the same type. And so by performing computation on one proof term, you finally get down to a proof term in which there are no applications. Well, okay, there's an asterisk there. But if you, every single time you apply something to a lambda, you reduce it by causing substitution. And if this process eventually ends where there are no more cases in which you're applying something to a lambda, then you will have another proof term, which we hope has the same type. And if it does have the same type, then this counterexample will no longer hold for that proof tree. Now, we don't have computation yet. I want to emphasize this. But there's this idea that if there were computation, then this counterexample wouldn't happen. If you, after performing computation, got down to an equivalence, got down to a, so the proof tree is going to be different. It's a different term. This proof tree right here that we just showed here is different from the proof tree for just the identity function, right?
Yeah.
So these are two proofs of A implies A. The latter proof, which is just lambda xx, that term, that's somehow a simpler proof. And somehow the proof terms simplify themselves. And our hope is that for the simplest proof term, this will always succeed.
So I guess like visually the way you could see it is that since the outer identity function is taken in the inner identity function, the outer technically has the type of the inner identity function, which is A to A, but we're always considering like the actual input to the exterior identity function, which is just the usual A to A. So it seems like the problem might arise because the identity function can take in whatever type it wants.
Right. So when we say that the identity function types to A in Racket as a contract, A there is a type variable for any possible type.
Yeah.
So here the actual propositional variables as A, they refer to concrete things. So A might here be it's raining outside. Then lambda xx is a proof term that can be interpreted as being a proof of it's raining outside, therefore it's raining outside, or of it's raining outside, therefore it's raining outside, that implies, therefore, that's the same thing that I said at the beginning.
Yeah.
So it's raining outside, therefore it's raining outside, bracketed, therefore it's raining outside, therefore it's raining outside. Lambda XX is also a proof term for that. So to say that lambda XX has type A to A, where A is a propositional variable, not a type variable now, is as correct as saying that it has type A to A to A to A. If A isn't allowed to stand for anything, but stands for a concrete variable.
Sounds
I
like
guess
it
in
makes-
contracts, you can consider A as the meta variable, as a meta variable for any type.
Sounds like it would make this into recursion.
But okay, so that's just a hint of one thing. We're not going to pursue this until we get to predicate logic. So we're not going to introduce computation yet. But this is one thing that I wanted to emphasize. Now, it's actually possible to get around this. You can introduce more rules so that any valid sequence is able to type check. And you're actually welcome to do this by yourself in Proust. But for the time being, there's a valuable lesson to be learned. You're constructing the proof system ourselves. And since we're constructing our proof system ourselves and choosing what rules to admit, we can hope to introduce only as many rules as we're going to be able to have a type checking system that's able to check every single valid sequence. It's not an uncomputable problem to check whether a proof is correct. In general, you can write proof systems in which that is the case, but you certainly are able to construct proof systems in which it's not an uncomputable problem. It's an uncomputable problem to find a proof for something, but it shouldn't be an uncomputable problem to read a proof for something and check if it's correct or not. For example, if your proof system is just checking proof trees and your proof terms are proof trees, then you should be able to determine which rule was applied at each step. And that should be a computable problem. But sometimes there will actually be a gap in some type systems for various reasons. Maybe they actually want to have an uncomputable problem, especially in programming languages. Sometimes programming languages specifications have uncomputable problems in the specifications. Java does this, for example. Haskell does this as well. Now, okay, that's getting a bit off topic, but this was one thing that you should actually keep in mind. And having this sort of gap here also introduces this proposed resolution where you actually perform computation. So that's a hint for something that'll come later. Any questions about that? So in other words, there are valid sequence for which type checking will fail. And here is one example. Okay, now today I'm going to go through the rest of the connectives. And the way that the rest of the homework in this class works is that it comes in pairs. One pair is to extend Proust in order to be able to handle those connectives. And the other pair is to use the proof assistant that you have just written to do your homework and to write other problems. So for propositional logic, there are 6 assignments that come in pairs. So there is dealing with ands. Then, sorry, and dealing with or, and dealing with nots. And for each one of these, there's a programming assignments. And there's a proof assignment. Now, for the programming assignments, what you have to do is you have to go into Proust and you have to look at how it handles the other rules, and you have to implement a handling of the rules that I'm going to give in today's lecture for each of these. And also, Proust has parsing functions and pretty print functions. So in order to do a programming problem, what this involves is adding structures for the proof terms and the types. For terms and types. Then it involves parsing and printing functions. So extending the cases. You're just extending those functions to handle these cases. And then finally, type checking and type synthesis. You don't have to write any entirely new functions. Each of these functions have match statements, and you have to add new cases to the match statements that handle the rules. Now, for predicate logic, when we switch to that, we're actually going to have a different version of Proust, and we're not going to implement those connectives in Proust. So the slate, these three programming assignments depend on each other. Each one builds on the previous, but then for predicate logic, the slate is cleared. So in other words, these three assignments are dependent on each other. You need to do the previous one before you can do the next one. And in a sense, you need to do the programming assignments before you can do the proof assignments. Well, the corresponding ones. So you need to implement and before you can prove results about and. And then the results about or will also use results about and the results about not will use results for and or. But for predicate logic, this dependence is cleared, and there's only one programming and one proof assignments. And these do not depend on the previous programming assignments. Although the programming involves modifying more functions. We'll explain the need of those functions tomorrow and next week. So it's highly recommended that you do these programming assignments, or at least one or two of them, before you do the programming assignment for predicate logic. And the ending goal in this class is to prove 0 plus n equals n, and maybe prove commutativity of addition. I'll add that as a bonus problem. So we'll be able to do the proofs that we did at the very beginning of the class over again in Proust that's actually capable of handling predicate logic and statements about numbers. And since I want everyone to get to that goal, it's fine if you don't finish all of these assignments before you start the programming and proof assignments for predicate logic. And if people are very stuck on the programming assignments, I might consider giving people the answers to the programming assignments if they give up on doing the assignments so that they can do the proof assignments. But I prefer not to. Any questions about that?
I just want to reiterate what you just said, see if I understand it.
Go ahead.
It's like the Proust, that document that we got from your email is incomplete in this sense, and we have to add things to it. So it's like we bought a basic game, and there are more DLCs coming up, and we have to buy them.
But you don't buy the DLCs, or you buy them by writing them yourselves. So it's a game in which the intention is that you write half of the source code.
Okay, good. Okay, thank you.
But you don't have to write any new functions. You just have to take the functions and you have to extend the match statements. So all of this is adding cases to match statements. So in other words, for example, there's going to be a grammatical rule for how we look at an and. Now, parsing isn't going to be able to recognize that rule at first, but you add a single line to the parsing statements, and now you can parse ands. Almost every single case can be handled by a single line. But there are a lot of cases. So you need to, for example, for and, you need to add 3 lines to parsing, 3 lines to printing, and 4 lines to the type checking and synthesis in total. Now, that's not many lines in total, but technically none of your other assignments were many lines in total. So line count isn't a good gauge of difficulty. I think that the assignment for and might be tricky, but when you start doing the other assignments, you'll find that you're doing exactly the same thing as you did before. In fact, when I was doing the programming assignment for predicate logic, I actually found it already tedious. I was thinking of maybe there would be a better way to automate those extensions because there are so many proof rules and for the very last programming assignments, and half of them are handled in the same way. So you're just copying things and then slightly modifying them. So the first one is going to be difficult, but afterwards, it's actually going to get a bit tedious, which is good. So you have to figure it out how to do this once. Although for the predicate logic programming assignment, you're going to have to do several other things that you didn't do with these assignments for reasons that we'll see. Okay, any other questions?
When will the next assignment due?
Oh, I'm going to post 6 assignments today. So these 3 programming assignments and these 3 proof assignments. And I'm hoping that you'll get some of them knocked out over the weekend.
Okay. By some of them, how many is some of them?
Okay, I want everyone to do the programming assignment for and by Saturday, and both the programming assignment for and the proof assignment for and by Saturday. And then hopefully you'll be able to, after you do this one, do 1 or 2 of the other programming or proof assignments. I'll probably make the first programming assignment due on Friday, so that people stay on task. I'll decide. Okay, I haven't decided the deadlines yet. Also, Prabhakar's notes are the best resource for this, and also he has documents about how to use Match. So I'll emphasize his document about how Match works, and I'll send that to you in an email. Any other questions? Okay, so let's actually get to logic. So now we're going to deal with the rest of propositional logic. So remember that what we had is we had the following. This is a slogan. You should repeat this to yourselves every night before you go to bed. The BHK interpretation of a proof of A implies B, or rather T implies W, is what?
Is a function which takes a proof of T and outputs a proof of W.
And one thing to note in the definition is that this is the BHK interpretation of a proof of. T implies W. This isn't the BHK interpretation of the logical statement T implies W. Rather, this is the BHK interpretation for what the proof term should be. And so this tells us that the proof terms, this suggests that the proof terms are lambda. Using lambdas as proof terms. Now, that's implication. So this is how the BHK interpretation deals with implication. Now, what about and? So the BHK interpretation of a proof of A and B, or rather T and W, is what? Any guesses?
So my guess is a proof of T and a proof of W.
Very good, exactly. So you prove a statement T and W by proving T and proving W. The BHK interpretation is this thing. You can think about it as the way we were talking about goals before and how goals change. In order to prove an implication, you prove the right-hand side of the implication after assuming the left-hand side and possibly using that in your proof. And then using that in your proof means you are able to construct a complete proof term after you fill in the gaps where your assumptions are. Then, okay, if we think about this type of logic, intuitionistic logic, it also fits in the framework of constructivist logic. In order to talk, you're not talking about proof, you're talking about constructions. And then how do you construct a proof of T and W? Well, you need to construct proofs for T and proof for T and a proof for W. And then you take those two proofs and you put them together and you get the proof of T and W. And so in the same way that the BHK interpretation for implication suggested what the proof term should be for implication, this also suggests what the proof term should be for ands, for proving and statements. Now, okay, well, there's a notation for it, and I'll tell you the notation in a second, but then can you guess what the notation should involve? Not what the notation should involve, what the proof term involves, really. Well, what should the proof term have in it?
Well, it should have.
Lambda?
Okay, go ahead, one of you.
He said lambda.
A lambda? Why?
Because I was thinking you have a proof of T, you have a proof of W, then you take some function of T and some function of W, then you somehow combine them. Something
Well, you have a proof of T, you have a proof of W, that's correct, and you somehow combine them is correct, but the word function doesn't really have a place in there, right? Because functions are for implication,
yeah.
but we don't have
Sure.
implication. So the proof term really should be something that just stores two proofs in it, right? Using pair-like structures, that store two proof terms. As proof terms. Does this make sense to everyone?
Yeah, because then the single proof term that contains the proof for T and W, it could be a proof of T and W.
Right. So now we had grammars for terms and types. I'm not going to switch color. Having an ellipsis at the beginning of the grammar means that I'm adding something to the grammar rules. If there's nothing and there's just an ellipsis, that means I'm just adding new rules. So it's the rules that you had before and then something else. So the new rule that we are having for types is we're introducing ands, right? So T and T should be a valid type. Then for the one new grammatical construction is this structure. And we're going to call this structure and introduction. So it's a proof term that lets you introduce and terms. And then it's going to be some proof term that has two other expressions in it, two other terms in it. And then also when we introduced implication, we didn't just have something that let us construct functions, construct proof terms for implication. It also told us how to use them, right? How did we use implications? Or in other words, what grammatical construction let us use proofs of implications?
The application?
Yes. So yeah, so the application lets us evaluate functions on values, or similarly, it lets us use a proof of T implies W and a proof of T to construct a proof of W. So in the same way that we have proof terms for how to construct ands, there should also be proof terms for using ands. And we'll get to those later. But first, let's give rules. I'm going to give, sure, I'll give monodirectional rules first. So in a context gamma, let's say that some term, so anything that has type something and something. Okay, no, here, we're going to give this rule. If you have an and intro, let's say T, W, and I claim that this has type T and W, then what should the premises of this rule be? What do I need to check in order to know that this introduction rule indeed has type T and W?
The proof term for T and then also the proof term for W.
So the proof term for T should what?
It should be a proof term for big T.
Yes. Good. So in order to check that these two proof terms, when you combine them in an introduction rule, proves T and W, you need to check that the first one proves T, and you need to check what else?
That small w is a proof term for big W.
Yes, exactly. That's exactly right. And so this proof rule is called the and introduction rule. So, okay, this is in monodirectional form. Now, how about using ands statements? So if I know A and W, what things can I conclude from that? Sorry, if I know T and W, what can I conclude from it?
That we have a valid sequence?
Well, no. I mean this as like I'm not talking about sequence right now. Let's just think of like a proof of an implication, right? A proof of implication is a function, right? I mean, that's not every single proof of an implication, but there are rules that let you say that function every single proof of an implication is going to be a function, but the proof term doesn't literally have to be a lambda. But let's say you have some function. How do I use that function?
Do I have to have a parameter and a body?
Sorry, what?
How do you use the function?
Yes.
How do you, in general?
Yes.
Oh, well, it needs an input, which produces then an output.
Yeah, so you use a function by evaluating it on an input, right?
Yes.
So the rule that lets you use functions is evaluation, or rather application. The grammatical construct of application is a construct that lets you, it's called an eliminator. It eliminates functions, it uses functions. Whereas the introduction rule is something that lets you introduce lambda. Well, the lambda introduction rule, lambda is the way to introduce proof terms for implications. Right. So then what is a proof of TNW by the BHK interpretation?
The proof of T and the proof of W.
So how do you use two proofs? Or no. Let's say it like this. What is a proof of, it is two proofs, but also the proofs are in a box. So you have a box and the box has a proof of T and a proof of W. How do you use that box?
Take either one of them out.
Yes. So that is precisely the thing. If you imagine the box being in the room, the first thing that you have to do in order to do anything with the things inside the box is open the box, right?
Yeah.
And when you open the box, let's say you only have one hand and the things are big, then you grab one of them. So to use a proof of T implies T and W, you use either proof, but before that you have to take them out of the box. And so the way that you take them out of the box is and elimination rules. And to be consistent with Prabhakar's notes, we're going to call the first factor 0 and the second factor 1. In computer science, array indices typically range from 0, although in lists in rackets, we call it the first element of the list. So technically in Racket, there actually isn't a precedent for starting indices at 0. But we're going to be consistent with Prabhakar's notes. So while functions only had a single introduction rule, abstraction, and a single elimination rule, application, and structures have a single introduction rule, but two elimination rules based on which one of the items you want to take out of the box. And so both of those take a single term inside of them, and that term should be a proof of an AND statement. Then let's write down what the proof rules are. So let's suppose that you have gamma. In some context gamma, we consider an elimination statement applied to some term. What letters do I want to use? I want to be consistent here. Let's call the proof term V. suppose I want to say that this has type T. What do I need to check in order for that to be true? From what does this follow? So this says that I've taken a box and I want to remove the zeroth item from the box V. When do I know that that makes sense?
Well, there has to be something in the box.
Yes, but here's an even better question answer. It has to be a box in the first place, right?
Mm-hmm.
How do you remove the zeroth item out of a function? That doesn't make sense, right? So it should be that it's a box. So in other words, we should check that V, we're now asking a question about V, right? So V should have type what?
T and W.
Yes, it should have type T. Why is T the first thing? Why not
Because
W and T?
we eliminate 0.
Yes. So this says that's the first factor. And I'm going to call them the first factor and the second factor. Again, really because I need to be consistent with Prabhalkar's notes because that's what we're using. So we're taking the first thing out of the box, and that's a T. And then in order to ensure that when we take the first thing out of the box and gets T, we need to know that the actual V is a box in which the first thing is T. And then we don't need to make any assumptions about the second thing. It's W. So the W that appears here does not appear in the T below. And this rule is called and elimination 0. And can anyone tell me what the and elimination 1 rule should be?
We replace the T with W on the on the bottom. Yeah.
And what's
And
the premises?
is the same thing. It's in context gamma we is a type of T and W.
Exactly. So these are the monodirectional rules. So and is nothing but a box with 2 proofs in it. In order to prove an and, you take 2 proofs and you put them in a box. That's the introduction rule. And in order to use an and, you remove things from a box. And in order to ensure that when you remove the first item from a box, you actually get T, you just need to check that the thing that you have is indeed a box in which the first item is T. Ditto the second item being W. So these are the 3 rules in monodirectional form that define proof trees using and. Now, okay, I'm going to edit the proof rules here. So first off, let's do the bottom 2 rules. Does it make sense to synthesize the type of V? Sorry, does it make sense to type check V against T and W? So if you're going here, if you're here, and you're trying to type check this, does it make sense to type check V as T and W?
No.
Why not?
Hmm.
Think about the implication elimination rule.
Can you please restate what the V is, where it came from?
Where v, little v.
Yes.
Okay, so we have a proof term, which is a and elimination applied to v. V is some term. It's a proof term. So it's a meta variable in the same way that t and w are meta variables. This is a little v. Does that make sense?
Yes.
So if you think about this as an action, this is saying I take the first item out of v. Now, so in order to check that that makes sense, you need to check, for example, let's suppose we were operating in checking mode. Okay, but so what is it that you're checking? And the thing that I asked you to recall was the proof rule for lambdas. So let's suppose that we have, sorry, for applications. Let's suppose that we have an application, f applied to a, right? What do we do here? In order, so I now want to do bidirectional rules. Okay, I'll do it like this. So if I just start here, then what do I fill in for t, right? That was a question that we encountered. The meta variable t appears at the top, but not at the bottom of this rule. So if we're working backwards and we're trying to do this, how do we fill in t? And what did we do as a result of the fact that it was ambiguous how to fill in t?
Well, we would have context to look it up.
Yes, and in order to actually be in a mode where we're doing lookups, what did we do?
We had to.
Well, what did we start discussing? This rule actually motivated the discussion of something, and what was that?
The B, the small b.
Oh, no, no, no. I'm talking way before. Before when
Okay.
we were talking about implication elimination. And we were talking about going into bidirectional rules. This motivated that checking wasn't enough. So what did we have to do with F?
Well, you mean after checking? Or is that the process you're talking about?
Well, we didn't check F.
No.
Instead of checking F, we did what? Anyone?
Synthesize F.
Yes. So we because there was not enough, there was more information on the top than at the bottom because the information of T was lacking. There wasn't a well-defined thing that we should check. So instead we synthesized the type of F. And then we type check A. There was a typo here, not against W, but against T. And that allowed us to synthesize the type of an application to the right-hand side of this arrow. So here, there's also more information at the top than on the bottom. So here we should operate in which mode? Checking or
Synthesis.
synthesis?
Synthesize?
Yes. Now, synthesis means, so we are not allowed to do checking because we don't know what W is here. Now, if synthesis succeeds, that means that there is a unique proof tree with this as its conclusion in monodirectional mode. And now, if it succeeds, that means we've proven that. So at the bottom, or should we be able to conclude synthesis as well? Are we be able to conclude that there is a unique proof tree, unique way to type this term? So the question is basically look at V. In order for the top line to succeed, V has to have a unique type. If V has a unique type, should the eliminator have a unique type? Also, think about it in the case of AND elimination. At the bottom, we were able to conclude synthesis because the application, there was no other way that you could type it. If there was no other way to type T, there was no other way to type F, then no matter what, F is a function that returns W, and the application is sensical. Then the return type should be W no matter what, right? So if no matter what, the box has T and W, no matter what, V is necessarily a box that has T and W. Then if you remove the first item, then no matter what do you get?
Get W.
Well, I'm okay. Yeah, except by the first item, I mean the zeroth eliminator. But yes, you get T. I'm going to call them the first and the second items. So you're able to synthesize here. Now, for and introduction, actually, let's say you're trying to do synthesis mode. Sorry, let's say you're trying to do type checking mode. So what do I need to do in order to check that this is a box with T and W? This makes sense as a box of T and W. Then what do I do? What do I put here and here?
Synthesis.
Yes. Now, at the same time, I can also consider a different rule. So if I'm trying to synthesize the type of an AND intro term, then what do I need to do? What do I put here and here? If I want to show that no matter what, that this proof term at the bottom, this box formation of T and W, no matter what, it must be understood as a box with T and W, then I must show that what?
T can be synthesized to T.
Yes, no matter what, T makes sense as T, and what else?
And W synthesized to W.
Yes. So in order to ensure that no matter what, this makes sense exclusively, as T and W, I need to make sure that T can only be understood as T and W can only be understood as W. I will actually somewhat confusingly call both of those proof rules and introduction. So and introduction has two versions, a synthesis version and a checking version. Whereas the and elimination, well, no matter what, the top of the rule has to have synthesis. So you may as well have synthesis at the bottom. In Prabalkar's notes, he actually gives two versions of these rules. One which has type checking at the bottom, but no matter what, the top has to have synthesis. The other version of the rules isn't necessary, because if you're trying to type check this, then what happens if you don't have a rule for type checking it?
We turn it.
Yes, we turn it and then we do the synthesis problem, and then you're able to make the same conclusion. So having a rule where you have synthesis here and checking at the bottom isn't necessary because you have the turn rule. So in fact, these rules right here tell you about how to synthesize and type check. And these two rules here tell you about how to synthesize and type check. So this together is a complete treatment of and. When you're implementing and on the programming assignment, you're going to have to implement 4 proof rules. And these are the 4 proof rules that you need to implement. And each one of these rules is handled by adding a single case to the match statements. So these are cases that you have to add to the match statements for what? This case. You have to add to which function? So there's type checking and type synthesis functions, right? This rule gets added to which of those 2 functions?
Checking function?
Yes. Whereas the other 3 rules, it's the conclusion that determines it. All of these 3 rules are about synthesis, right? I mean, yes, exclusively about synthesis. But in the same way, implication elimination, which had mixed synthesis and checking, that was a proof rule about synthesis. It is a proof rule about how to synthesize the type of an application. And so the other 3 rules get added to the function for type synthesis, whereas this gets added to the function of type checking. And each one of them is a single line that you add to that match statement. Any questions about that?
Do you mind summarizing again what the match function does?
That's not relevant right now. I'll send you a document that explains that. But okay, I can give you half an answer to that. So in the code, we're going to have structures. For example, we're going to have a lambda structure, and we're going to have an and intro structure, and an and eliminate. So here, actually, if you look at the grammar, I added 4 new grammar constructs. 3 new grammar constructs to the grammar for terms, and 1 new grammar construct to the grammar for types. So the first thing that you do when doing the implementation is that you take these new grammar rules and you introduce new structures for them. Now, that's actually very easy because, for example, if we thought about how we introduced nats, in order to define nats, here's all the code that we wrote for defining nats. We wrote in bracket structs z, open paren, close paren, and then you should also write a hash transparent. And then, oh, you actually, sorry, define structs, define. And then define structs. S, and then here val. Well, then in match statements, all of our proof terms and our types are going to be inside structures. So, for example, the type synthesis function is a function that takes a context and a term, right? Then both of these functions are structurally recursive on the proof term, right? Do you agree? Are you following me so far?
No, I don't get that last part, how it's structurally recursive on the proof term.
Okay.
What do you mean by that?
Let's look at this. Suppose you're trying to do this synthesis, right? Sorry, I should not make that blue. Suppose you are trying to do this. Then what rule applies? Well, I mean, how did you know that, for example, here? How did you know that this rule had to be implication elimination? Well,
Did we say because we have lambdas?
not because we have lambdas.
No.
This isn't a lambda. This expression right here is not a lambda. Which type of expression is this?
It's an application.
Yes.
Oh, you're right.
You see
Okay,
that?
I see it.
So because this is an application at the top level, what is this? At the top level, this is an application, not a not an abstraction. Because it's an application, you have to use implication elimination. Now here, what was the proof term? What kind of grammar variant is that? Martine, which,
But that is a lambda, right?
that is a lambda. So which rule do you use?
Okay, this the second one, it's the introduction, implication
Yes.
introduction.
Now, what about this? What type of grammar variant is this?
The variable,
So which rule do you use?
the variable rule.
Yes. Now, okay. Now, type checking and type synthesis are functions that take a context and a proof term, and then type checking also takes a type. So suppose you are trying to type check a term which is a and intro term. Then which rule do you use?
Doesn't it say right there, the and?
Yes. So we
Introduction.
introduced 3 new grammar constructs, right? We introduced 3 new grammar constructs. And we introduced 3 new rules. Except for the fact that one of these rules has both a synthesis and a checking mode. But apart from that, we consider those 2 rules as sort of the same. Each grammar construct has a unique rule corresponding to it, right? Except one of these rules really has a synthesis and a checking mode. But if you're in synthesis or if you're in checking, then there aren't 2 ways to check the type of an and. There's a unique proof rule that applies. And how do you determine the proof rule that applies? What do you do? What do you look at in order to determine which rule applies?
So the context.
Not the context. No, definitely not the context. It's, to say that you're looking at the context would be to say that let's look at this here. Which rule, which proof rule did you use? Why are you using implication elimination here? Did you look at the context to determine that you should use implication elimination?
No, because of the syntax.
Yes, so that is the proof term. Well, everything is syntax, but you looked at the structure of the proof term, right?
Yes.
So here, in order to determine which proof rule to apply, you look at what?
We do the same thing.
Yes, you look at the structure of the proof term. So in other words, if you're trying to, for example, synthesize the type of some term in some context, what do you do?
We need to look at the structure of the proof term.
And that tells you exactly which rule to apply, right?
Yes.
So what is the programming implementation of the type synthesis function? It's a match statement, and then it has cases for every single possible grammar variance that the proof term could be. Does that make sense?
Yes, that gives a good description. Thank you.
Right. So I can actually show you, let me quickly open. Actually, let me open the version of Proust that does not have holes in it, because that's shorter. So here is the version of Proust, which, does everyone see that? Let me increase the font a bit.
Yes.
Okay, so this is the version of Proust, which is the basic version. So this doesn't have holes in it. So variables we're going to represent with symbols. Does that make sense? That's just a statement. We're going to represent variables with symbols.
Okay.
Okay, now lambdas and applications are two structures that we have for expressions, right? We're also going to have something called annotations, but don't worry about that for now. So we're going to introduce two new structures to store proof terms that are lambdas and to store proof terms that are applications. And then we're going to have one new structure to store types as arrow types. Now there's a function for parsing, for example. Parse just checks the syntax of the expression and then constructs the appropriate structure recursively. Similarly for printing, but that's not what we care about. Let's look at the type checking and type synthesis rules. So let's look at the type synthesis rule. How do you synthesize in some context, the type of some expression? So let's look at the statements. It's a match statement. It looks at the structure of the expression. If it's a lambda, then what? How do you synthesize the type of a lambda?
You cannot do that.
You cannot. So if it's a lambda, you throw an error. Now, if it's an annotation, okay, well, you type check, but I haven't discussed in detail how we deal with annotations. Let's say applications. How do you type check an application? Sorry, synthesize the type of an application. So this is the rule for implication elimination, right? This case of the match statements, what is implication elimination? The rule tells you how to synthesize the type of an application, right? Martine, does that make sense?
Yes.
So this here is an implementation of implication elimination. First off, implication elimination is a case in type synthesis. Implication elimination tells you how to do a certain type synthesis. It tells you how to type synthesize what kind of term.
Okay.
How do you know when you use implication elimination?
Well, you have to match the
Okay, but
the
not in
syntax.
match terms, just
Oh,
in,
okay.
in colloquial terms. How do you know that the rule implication elimination applies? Not in programming, just regularly.
Well, as people, we can look at it visually.
Well, you look at the proof term, right?
Yes, we look, yes.
And what kind of proof term does it have to be?
It has to have it looks a certain way, so it has to have a
Not
function.
it looks a certain
No,
way. Proof
no,
terms
no.
have different kinds and they have names. There are lambdas, there are variables, and there is what?
Okay.
What is the third kind of proof term for implications?
Application.
Yes.
Application.
So in other words, implication elimination applies to proof terms which are what?
Applications.
Yes. So in other words, when you're trying to synthesize the type of some term, you have a case for applications. And the case for applications in the match statement is the implementation of the implication elimination rule. Does that make sense?
I follow.
Right. So for example, in the first assignment, you're going to have to implement and. Now there are 3 rules for how to synthesize the type of an and statement, right? And they depend on the type, the grammar variant that you have. Now for each grammar variant, you're going to define a new structure, like we defined a structure for annotations and a structure for applications. And like we defined a structure for lambdas. How do you type check a lambda? Well, right here, this right here is an implementation of the implication introduction rule, because that tells you how to type check a lambda. And then the else statement right here is an implementation of the turn rule. Although you don't have to implement turn because it's already implemented. You're going to have to implement 4 rules, 3 type synthesis rules, 1 corresponding to each grammar structure. And then the and introduction rule also has a type checking version corresponding to it. So you're going to have to add 3 new cases to the type synthesis and 1 new case to type checking. Does that make sense?
Yes.
Okay. So that should answer your question about what does match have to do with it completely, does it?
It does.
Okay, good. So now let's do some examples. Let's actually do some examples of proof terms. And you're going to actually see that proving things is very intuitive. It's so you sent me many questions by email asking about Proust. Proust is not the issue isn't understanding Proust, it's understanding the rules and how to write proof terms. You are able to write proof terms completely outside of Proust. Proust checks proof terms. It also provides a way to build up proof terms piece by piece, but you can also just give the proof term in one going the whole hog right away. And we're now going to see how to reason about proof terms. So here are some proof terms that I have. Okay, remember also that if you have anything like this, let's say A implies B implies B implies A. Sorry, it implies B and A and B. So first off, what does this means is implication is right associative. So really what this means is this. And then and has higher precedence than implication. So you're trying to prove that A implies B implies A implies B. So you want to write some function that takes a proof of A and returns a function that takes a proof of B. And then once it's taken a proof of B, it returns a proof of A implies B. So how do you write such a proof term? What's a proof term for this? In the empty context, what proof term do we do? How do you write a function? Anyone?
Lambda.
Sure. So what is lambda taking here? I mean, what are you actually going to feed it when you use this?
Letter.
Well, okay, that's a variable, but that variable when you use this is going to take a proof of A, right? So we may as well call the variable little a. That's a good letter to use. And then what does the lambda return? What's the body of the lambda?
B implies A and B.
That's not a proof term.
That's the goal.
That's a type. That's a proposition. What's the proof term? What's the body of the lambda? That should be a proof term.
Another
So
lambda.
we want to prove B implies A implies B. How do I do that?
You need another abstraction. So another lambda.
Yes. And so this takes the proof of B. So if you think about this proposition intuitively, what it says is if you have a proof of A, then if you have a proof of B, then you can put A and B together in a box. You can put proofs of A and B together in a box. Oh, I think that might actually be helpful for people who are having difficulty parsing statements with multiple implications. Colloquially, what this logical statement reads as is if A, then if B, then A and B. Right? So logically, the statement says that if A, then the following statement is true. If B, then A and B. Right? Does that help anyone?
Yes.
Okay, well, okay, if you have A and B, but now in proof worlds, if you have a proof of A and you have a proof of B, how do I make a box that has two proofs in it?
An and intro.
Yes. Then what?
Little a and little b.
Right. So, and this has type what?
A implies b implies a.
Well, not, the last thing was,
A and B.
So, but if you actually think about it, this is very, very intuitively clear because it's saying you want to, in the end, produce a box that has a proof of A and a proof of B. Well, if you take a proof of A and you take a proof of B, how do you do the thing that you want? You put them in a box, and you put them in a box with the and introduction term. It's a box that contains both of them. Okay, well, now let's look at the elimination rule. So the statement that we had before was sort of obvious. What about this one? A and B implies B and A. So if I have a box that has proofs of A and B, how do I make a box that has proofs of B and A? Don't think about this in proof term language. Think about this in literal language. You are in a room. The room has a box. The box has two items in it, but the box sort of has two compartments. It's clear which item is the first item and which is the second item. So if you have such a box, how do you produce a box that has the items in swapped order? Literally, you're in the room. So yeah, so think about, yeah, actually let's do this. Let's draw it like this. This is you. And here is a box that has inside of it a proof of A and a proof of B. How do you go about switching the positions of those two items?
Well, you have to open the box, take one out, take both of them out, and then put A in the place of B and B in the place of A.
Okay, now as a proof term, well, first off, we started off by supposing that we had a box with A and B, right? So what is the supposition? What's the proof term for using hypothetical reasoning? How do I prove the implication? What do I start my proof term with? Like Martine, so look at the proof term that we had before, right?
Mhm.
A implies B implies A and B. How did we take A in as an argument? What did we do?
We have a proof term A for an abstraction.
Yes, so we form an abstraction where what are we sort of assuming? We're assuming a proof of A and B, right?
Right.
So let's call that C. Okay. Now you said that you take both items out of the box and then you put them back in the box with swap positions. So now when you write it in the opposite order. What's the last thing that you do? What is the very last thing that you do?
You mean at the end?
Yes, at the end.
You mean you would close the box?
Yes. So you put the items in the box. How do you put items in a box? It is a proof term.
In parentheses and intro.
Yes. Okay, what's the first item that you put in the box?
B.
And how do you get B?
Abstraction.
No. How
No,
do you get B? No, like think about yourself in the room. Right now, you don't have B. You have a box that has A and B in it. How do you get B?
Okay, well, I open this and I take B out of the compartment.
Right, so you get B by taking B out of the box. How do you take B out of the box as a proof term? So looking here, how do you take B out of the box?
I had an elimination.
Okay, and you're doing it on the second factor, right?
Yes.
And what did we call that? Elimination what, 0 or 1?
Does it matter?
Well, yes, it does, because 0 says that you're removing one and 1 says that you're removing the other. There are two different eliminators.
Okay, you mean like first and second?
Yes, except we call them 0 and 1.
Okay.
So which eliminator are we using? Do I put a 0 or a 1 here?
We're going to take 0. We're going to take A out first.
Well, actually, let's think about this. Look at this. This says we are putting things in a box.
Mhm.
What are we trying to do? We're trying to produce a box that has what?
2 proofs.
Yes,
One
what's
for
the
A,
first one?
for B.
Okay, so here you're putting things in a box. What are you putting in for the first components in the box?
The B.
Yes, so how do you get the B?
Well, okay. We did an elimination, right?
Yes, which eliminator do you use to get B?
1.
Yes, on what? What are you using that eliminator on? You need to put a proof term here. What proof term goes here?
Okay.
How do you, what is
it in a, it's okay.
what is the box with A and B in it? You assume that you have a box, right? Well, you gave that assumption a name. What was the name of that assumption?
Little B.
What did you say?
Oh, is it the little B? No.
There is no little b. Look at this proof term. Little b doesn't make sense. What is little b? Look at the proof term above it. You had little a and you had little b. Why did little a make sense? What was the meaning of little a? At the end, you were producing a box with a proof of a and b, right? What was the meaning of little a?
Proof for A.
Yes, why? Because that's what you have here, right? Yes?
Yes.
Okay, so what is the name of the box that has A and B in it?
It has the abstraction for A and the abstraction
No,
for
what is
B.
the name of it?
No.
We're writing a proof term. Well, how do we start our proof term? We said we're assuming something and we're giving it a name. The name was C, right?
Mhm.
We chose C arbitrarily. So what does C mean? C means a box that has A and B. So the thing that we put here is we take the second item out of C, right? Does that make sense?
Okay.
Okay, and so what do I put here for the second factor?
Okay. Elimination 0.
On what?
It's still C.
Yes. So that's the proof term. So I'm giving you a construction. What is an abstraction anyway? Like I ask you, for example, to square 2. You say, oh, how do you square 2? Well, you take 2 and you multiply it with 2 and you get 4, right? So now if I ask you to square 25, you're going to know how to square 5, you're going to know how to do that as well. How do you know how to do that? Because you have an idea in your head that there's a process for how to square a number. You multiply it with itself, right?
Yes.
So what are you doing here? You're proving that A and B implies B and A. So in other words, in logic, you're showing that if you know A and B, then you also know B and A. Now, in intuitionistic constructivist logic, you're actually showing how to change a proof of A and B into a proof of B and A. Now, how do you change it? Well, a proof of A and B is a box that has A and B in it. So you take the first item out, you take the second item out, you swap their positions and you put them back in, right? That is an abstraction of a process that works for any box that you give me. So for example, A and B can have different proofs. But no matter what, if you give me a box that has proofs for A and B in it, then I have this abstract process of I take them out, I swap them, I put them back in, right?
Yeah.
So you're forming instructions for how to do that. In order to form instructions for how to do that, you say, well, your instructions have an input, right? You start with a box that has a proof of A and B, right?
Yes.
And then what do? Well, the results is you're going to put two things in the box. What are they? The first thing that you're going to put in the box is what you get by taking the second item out of the box. And the first thing is what you get by taking the first item out of the box. Technically, the two boxes are different. You're technically constructing a new box. You can take the item out of the box multiple times, for example. They get replenished. It's not like you're actually modifying the box. But this is what an abstraction means. It is an abstraction of this process. You formed instructions for how to do this. And so this right here, this program, this is a proof term, but you can also think of it as a program. Okay, and what type does this program have? What were we trying to prove originally?
A and B implies B and A.
Yes. So what we have right here, is this helping?
Yes.
This is a program that gives instructions for how to swap the order of things in a box. And that instruction set is a proof of A and B implies B and A. So first off, A and B is the logical statement. For example, A might be it's raining outside, B might mean it's Tuesday. So the logical statement is it's raining outside and it's Tuesday implies it's Tuesday and it's raining outside. Now that's a logical statement. Now in proof worlds, a proof of A implies B is a proof, well, a proof that it's raining outside and it's Tuesday is a proof that it's raining outside and a proof that it's Tuesday. So for example, a proof that it's raining outside could be I look out of the window. And a proof that it's Tuesday could be I look at the calendar, which presumably I've been marking off or somehow tearing things off. And then, so this tells you how to go from one proof to the other proof. Okay, does that make sense?
It does.
Good. So let's take a break and then I'm going to do or and nots. But so this is called intuitionistic logic, and really in a certain sense, it is intuitive. Instead of going through Boolean tables and other things, it's very literal how to do instructions on how to do things. This is how you think about logic in this class. Okay, so let's resume at 3:38. Or actually, I'll take questions first. Any questions? Okay, resume at 3:38. Okay, let's resume. So I'm going to, any questions, by the way? So I'd now like to do cover the first problem on the assignments, on the first Proust assignments. I guess this is a homework spoiler for that one. So suppose this is you. And now suppose that what you have is a pouch of coins. Don't overthink the pouch part. They're just coins. You don't have to remove them from the pouch or anything. And you have in the room 2 vending machines. And the first vending machine has walnuts. And then the second vending machine let's put panels there, has walnut crackers, nutcrackers. So these are shelled walnuts. And these are walnut crackers. And then walnuts have food in them. So how do you get food? That's the question. Martine, are you there?
Yes, I'm back.
Okay, how do you get food?
I have coins. Oh, shit. So the shelled walnuts, they're all, they won't eat crackers because they're ready to eat. Is that true?
No, they have a shell. You can't eat
Oh,
them.
they
They're
have
not food.
shells. Okay, sorry. Okay.
Oh, I guess shelled could mean de-shelled. No, but I mean they have a shell.
Okay. So I walk up to the first vending machine, say shelled walnuts. I put in the coin. I get a bag of shelled walnuts. I can't eat them. So then I have to walk to the vending machine with the walnut crackers. I put in a coin. I get a cracker. I open my bag with the walnuts and I crack a walnut, and now I can eat what's inside.
Okay, good. Let me, my tablet's running out of battery. Swap that in. Okay, so let's introduce the following things. Let's say that coins have type C. So coins have type C. Then walnuts. Sorry, coins have type A. Walnuts have type B and food has type C. So then what is the type of a walnut cracker? What does a walnut cracker let you do? What's the input to a walnut cracker?
It gives, given B, we get C.
Does that make sense, Martine?
Yes.
Does it? Martine?
No. What did he say? I'm sorry, I couldn't hear him.
He said a walnut cracker takes a walnut and gives you food, right? So walnuts can be considered as having type B to C. They
Right.
convert walnuts into food, right?
Yes.
Okay, now what does the vending, okay, what does the walnut vending machine? What type do walnut vending machines have? Martine, tell me.
What type?
Yes. What do they take and what do they give?
They take in A, something of type A, and
A coin?
they return something of type B, the walnuts.
Yes. Okay, what do walnut cracker vending machines? Have type what?
It takes something of type A.
They take a coin and what do they give?
They return.
Well, after you give a coin, what do they give you?
The cracker.
A cracker, right?
The,
And so what type does crackers have?
B goes to C.
Yes. So in other words, walnut crackers have type A to B to C, but by our conventions, we write that as, we exclude the parentheses and we just write A to B to C. It's understood that the parentheses work that way. So in other words, remember that we started off with coins and 2 vending machines, right? And we were able to get food, right?
Mhm.
So let's think about the assumptions. So let's say our first assumption is that we have a walnut cracker vending machine. So that means that we should have something of type A to B to C. That's the first thing that we have. The second thing that we have is a walnut vending machine. So that's A to B. And the third thing that we have is coins. And from those 3 things, we should be able to produce food. So when I asked you, you're in a room with coins and these 2 vending machines, how do you get food? What you have just provided me with there in saying how you answer that is a proof of the following proposition. So let's think about this proposition. I'm going to rewrite it below. The proposition is A to B to C. I put explicit parentheses here. 2 A to B to A to C. Now, the way that parentheses work is that there are some implicit parens. I put implicit parens here, and I put implicit parens here. And I guess there are also implicit parens here. So what this says then is, if I have a cracker vending machine, then if I have a walnuts vending machine, then if I have change, I could get food. Does that make sense?
Yes, it does.
Okay, now how do I prove it? So first off, the statement had 3 ifs, right? So how do I suppose that I have those 3 things? How do I suppose something? What proof term do I write? So what's the first thing that I'm supposing that I have? Look at this type. Let's look at this type. It's an arrow type, right? What is it at the top level? It's an arrow. Here is the left-hand side. Here is the right-hand side, right? So what am I supposing first?
Lambda of something like
Yes.
x.
And what am I really supposing in this situation in the room? I'm supposing that I have what? Martin.
I have,
The walnut cracker vending machine.
Right. So let's say I just give that assumption a name. Let's say give it a name X. Right? Then what's the second thing that I'm assuming? So now I'm trying to prove the right-hand side on this. Now let's look at the right-hand side. The right-hand side is also an arrow. Here is the left-hand side. Here is the right-hand side. So what is the second thing that I'm assuming that I have? In colloquial language, in this walnut analogy, what am I assuming? What follows the second if?
It says the walnut vending machine. A goes to
Yes.
B.
So I assume that, and I make that assumption be, let's say, Y. And then what's the final thing that I'm assuming? That you have what?
I can get, it says A to C.
What is A? Look at this informal thing
It's
that I
the
wrote here.
coins. The coins.
Right. So you're assuming that you have coins. So that's the last right-hand side. This is now the right-hand side. And this is now the left-hand side. And so I'm going to call that assumption Z. So notice how there are a bunch of arrows in this proof term, but it's not as though I assume every arrow. I just assume at the top level, the left-hand side of whatever arrow I have at the top level recursively. So all 2 of these arrows got eliminated by just the one assumption that I had here. So I assume that I have X, Y, and Z, where X now has type what? What type will X have? What is X? X is a cracker vending machine, right? So what type does X have?
A implies B implies C.
Yes. Now what type does Y have?
A implies B.
And what type does Z have?
A.
Right. Okay, Martine. Now, how do I, so let's look, you told me how you get food. What's the last thing that you do in order to get food?
I have to crack the shelled walnut.
Yes. Now, cracking something is using something, right? So what's the proof term for using something? Sorry, for using a device that accomplishes something. You're using a function, right?
Mhm.
So what's the proof term for that? Don't look at notes, think. What's the proof term for using a function?
Well, it looks like an application, right?
Yes. So at the top level, after making those three assumptions, you're going to form an application. Now, what are you applying to what?
I applied my cracker to the walnut.
Good. Okay, how do you get a cracker?
I had to get it from the walnut cracker vending machine.
Okay, so the cracker vending machine is also a function, right? So what's the proof term for putting a coin in the vending machine?
I'm sorry, what is that?
What is the proof term for putting a coin in a vending machine?
Okay.
No, the proof term for it. So remember that your vending machine is called, your cracker vending machine is called X, right?
Was it
Your
C?
coin is called Z.
Mhm.
How do you put the coin in the vending machine?
It's an input to function.
Yes, okay. So it's an application. And what are you applying to what?
I have to apply Z to the walnut vending machine.
Okay, okay, we say, I'm not sure if I've been saying it right, but I say you apply the function to the input. So what's the
Okay.
function? It's the vending machine. What's that? What do I call? What's my name for the vending machine?
Was it Y?
No, Y is the vending machine for walnuts. What's the name for the cracker vending machine? What did you say? Well, it's not Y, so what's the other one?
What? X.
Yes. And what do I apply to X? I apply X to what?
Z.
Okay, so that's how I get a cracker. Now, how do I get a walnut?
Okay. Apply Z to
Well, what's the first thing that I write?
the function
Which is what?
Y.
Okay. And what's the...
Z.
Yes. Okay, so this proof term right here encodes the process of if you have these three things, you put a coin in the first vending machine, you get a walnut, you put a coin in the second vending machine, you get a cracker, then you use the cracker on the walnuts. Right? So that's what this proof term says. So this proof term right here is a proof of A implies B implies C implies A implies B implies A implies C. Notice how it was not at all hard to come up with the proof term when you thought about it like this. If you thought about it like this, if you're in a room with coins and 2 vending machines and you're hungry and you want food, then it's obvious what you have to do, right?
Mhm.
Like intuitively, it's absolutely clear how you get food, right?
Yes.
Well, this is the same thing. You have something that when given something of type A gives you something of type B to C. And then you have something when applied to something of type A gives you something of type B. And then you have something of type A. How do you get something of type C? Right?
Yes.
Okay, did this help?
Yeah, and so just looking at the syntax, so you have 2 applications inside of an application, the X.
Yes.
Z.
Well, okay, so by the syntax, an application is some expression applied to some expression, right?
Mhm.
So I have 2 expressions. Each one of those expressions has to be some lambda calculus expression. Now, incidentally, both of those expressions are themselves applications. So an application is always some expression applied to some expression. There are 2 slots in an application. This is what the first slot is filled in with in this case, and this is what the second slot is filled in with in this case. But every single application is always something applied to something. Any more questions? Did this help anyone else?
Yeah, I love this example. It helps him a lot.
Mm. So really, this type of logic that we're doing, it's very pleasant type of logic. Writing proof terms, Proust lets you develop them piece by piece. So it lets you, what will Proust do, for example? You'll start off with in Proust by having something like, there will be holes. Holes are promises, so holes type check to anything. So you're starting off with, for example, a hole type checks to that type. Then you refine the hole to be, let's say, 3 nested lambdas, lambda x dot lambda y dot lambda z. And then the body, we're going to put a question mark. We don't know what the body is yet. And let's say we're trying to type check that against. So first off, that should be something, well, it's the term itself. Yeah. Now, Proust will know that whatever goes in for the question mark has to be a proof of C in a context where you have 3 assumptions, where X is bound to this, Y is bound to this, and Z is bound to this. So to give a demonstration, here is implication with holes. So this is how I develop the proof interactively. I'm going to set the task, and then I'm going to write what the proof term is. So that was A implies B implies C implies, oh, and I need spaces. That's important because in brackets, the name will, it's fine if it has an arrow inside of it. So that'll just be a single name if I don't have spaces. It's fine not to have spaces after parentheses because Racket parses that, but it's better to put them in anyway. And then A, and then C. So that's my proof term. Sorry, that's not my proof term. That's the type. That's the type for which I'm trying to produce a term. Ah, I need to put an exclamation mark after set task because it uses mutation. Whoops. Okay, so that's my task. Now, right now, a whole is a promise. So I can also say, for example, print context or print goal. What is it? Print goal. So what am I trying to do right now? Goal 0 has this type. I'm supposed to fill in question mark 0 with something of this type. Well, I'm going to write half of the proof term. So I'm going to assume that these three things. So I'm going to refine 0 with a proof term, which is a lambda. And then it's also going to be another lambda. And then it's also going to be another lambda. Whoops. I also need this. And then I don't know what the body of is going to be. So I'm going to refine that. And then Proust will take this question mark. Refine just replaces the question mark with this thing, but it also checks that that's something legal. Well, it is legal. And the question mark then has to be replaced with some term of type C in a context in which I have these three assumptions, right? Here is my X, here is my Y, here is my Z. Now I could just refine it to be the answer, but I can also develop it interactively like this. I need to produce something of type C, right? So that's eventually going to be given by applying something of type B to C. Now, how do I get something of type B to C? Well, I take X and I use something on it. So that gives me something of type B to C. And then on this, I also need to feed it with something. So I can put two question marks in it there. And then, so it'll replace that question mark with the term that I've asked it to replace with. That's what refine does. It numbers the new question marks, and it tells me now I have two goals. Goal 3, I'm supposed to give something of type B. Because if I give something of type B to this term, then I'll get something, goal 2 has type A, goal 3 right here has type B. That's what I need to feed into the B apply C machine to get something of type C. So goal 3, something of type B in this context. Well, how do I do that? So let's look at the context of the third goal, which is right here. I have these X, Y, and Z, and I'm trying to do something of type B. Well, how do I do that? How do I get something of type B here? Anyone?
You do YZ.
Yes. So Y is a function that takes something of type A and returns something of type B. Z is something of type A. This gives me something of type B. Done. Okay. Let's now look at goal 2. That's the only remaining thing that I have. If you look at the proof term, goal 3 was a question mark. I refined it. It got replaced with that. Now, the only thing that I'm missing is this, and I just need something of type A. So I'm going to refine goal 2. And how do I do something of type A?
Just Z.
Yes. Yeah. Now, in order to make it a proof term, the proof terms for variables, In Racket, they're symbols. So I do quote Z. And that completes the goal. And now I have the proof term. So that's how I would develop that interactively. In general, if you have proofs that have implications, a series of implications, it's frequently useful to just start your refining by assuming all of the top level implications, assuming the left-hand side recursively. Because, for example, I showed you this before, but Racket we have like parse types functions. So what happens if I parse this type? It'll give me actual AST structures. So what is this AST structure? Now that I've pasted it in here, I have the benefits of having highlighting. So what is this? This is an arrow. It has a left-hand side and it has a right-hand side. When I click between them, they are highlighted. So when I parse this type and I see that it's an arrow at the top level, this is the left-hand side, this is the right-hand side. I'm going to assume the left-hand side. I'm proving the right-hand side. What is that? That's an arrow. It has a left-hand side, it has a right-hand side. I'm going to assume the left-hand side, I'm proving the right-hand side. What is this? It's an arrow. It has a left-hand side. I assume that's. So that's why I start with 3 lambdas. And then eventually I'm just proving C. Okay, back to the notes and doing the other connectives. Whoops. So that was me being distracted for a while and discussing this. Now let's get back to the actual meat. So is that clear for everyone? And then you should also read Prabhakar's notes. This is all explained in there. The notes are our textbook for the second half of the class, so you should be reading them. Okay, let's do ORs now. So the BHK interpretation of a proof of T or W is what? Anyone?
It's a proof of T or a proof of W.
Yes. So what does that suggest that the proof term should be? Just not syntactically what it is, but really what are the proof terms for ORs? So how do you prove an OR? How do I prove T or, so for an AND statement, in order to prove T and W, I needed to prove T and I needed to prove W, and then I needed to put those together, right? How do I prove an OR statement? What are 2 ways that I can prove T or W?
So it's got to be either a proof of T or a proof of W.
Right, but so what is one way? But that's 2 different ways to prove it. So what's one way to prove T or W?
So a proof of T.
Yes. So one way to then this says, and what's the other way?
A proof of W.
Yes. This suggests, rather, that there should be 2 introduction rules. That there should be 2 introduction, that there should be 2 proof terms for introduction. specifically one for proving T, one for proving W. So now we're going to add to our grammar. So for terms, and then for types. So for types, we're going to have a type of or statements. That's pretty self-explanatory why we add that. And then for introduction, there should be two introduction constructs. I guess the BHK interpretation, it has something that's a bit vague in it. Implicit in saying that a proof of T or W is a proof of T or a proof of W is the idea that we should be able to tell which one of the two things you're proving. So it doesn't just suffice to hand me a proof and say this is a proof of T or W. You have to hand me the proof and say this is a proof of T. Or you have to hand me a proof and say this is a proof of W. You can't just hand the proof without telling me which one it is. And so the two structures for that are respectively called or intro 0 and or intro 1. So maybe think of a or statement as a box that's wrapped up in paper and then you don't know what's inside of it. It's a gift that you're given, but also it tells you, okay, but it tells you which one of the factors it's including in. So both of these are expressions that you can form in 2A. And similarly, there's also going to be an or elimination term, but we're not going to say that yet. We're going to get to that in a second. So now let's give the proof rules. So suppose in some context, I have one of these terms. And let's say that this term has type T or W. Then in order to check that that's the case, well, what would this follow from? So I'm handing you one thing, and I'm saying that it's the first thing in a proof of T or W. How do I check that what you've given me is actually that? No. Anyone?
We check whether T is a proof of T.
Yes. So for now, we're not saying checking. For now, we're just saying if we know that T is a proof of T, then we know that or intro 0T is a proof of T or W, right?
Yeah.
Does this rule make sense to everyone? Any questions?
Yes.
It makes sense, or you have a question?
No, it makes sense.
Good. Okay, so tell me what the proof rule here is then. So this is a proof of T or W provided what? Martine, what is the hypothesis of this rule?
So
Go ahead.
okay, so we'll have the same as above, except for little t, we would have little w. Is the
And
proof
that
term
should be a proof of what?
the big W.
Yes.
VI1.
So this is or intro, sorry, or intro 0, and this is or intro 1. So there are two introduction rules, and then for ands, if we look at this, the two rules also had names. The two elimination rules. There were two elimination rules. And elimination 0 and elimination 1. And then a single introduction rule with two different versions when we considered synthesis or checking, but really it's the same rule. So the proof rules that corresponds to the grammatical constructs, remember, it's grammar constructs that dictate which proof rule we use if we're working backwards from the tree. So the proof rule that corresponds to the or intro construct is the or introduction rules. And then there are two intro constructs and there are two introduction rules. Now, here's the tricky question. How do I use a proof of T or W? Sorry, T or W. So this is a harder question. Any guesses?
We have to do it either way. So it can be a proof of T or it can be a proof of W. So we need a way to handle both.
Yes, very good. So remember that when we had a proof of T and W, we used it to prove something else, right? We used it, for example, to prove T. That was a single goal. So in order to use an or statement, there should be a single goal that you're trying to achieve, right? So let's say you want to use an or statement to prove something like V. Then what do you need? Oh, well, okay. Here, but I don't remember any very appropriate versions of the joke to put in. I only remember the one that I've most recently seen on Facebook. So there are Venn diagrams. I would go with a more appropriate version of this joke if I remembered it, but there's this one. Excel and then incels, and then mistakenly assuming that something is a date. And so you have this conclusion and it follows from two different things. But you don't know, you're given something or something. That something or something might be one thing or it might be the other thing, but you'd like to conclude a common thing from them. So what do you need in order to make that conclusion? Well, you said it, right? You need a way to handle both cases. And so how would you conclude something from something. So if you have T, then how do you conclude V from it? What do you need to conclude V from T? So in other words, if you're handed either an Incel or the Microsoft Excel program, how do you conclude that that thing is going to mistakenly assume something is a date? You don't know which one of the two you're handed. Okay, let's put it like this.
We
So
need a proof of,
go ahead.
like, I think I know. We need a proof of T implies V, like something like that.
Yes. And you also need a proof of
W implies V.
yes. So in other words, to use an or statement, you need three things. You need a proof. What's the first thing that you need?
We need a V.
Well, you need a proof of, so remember, for example, look at the AND elimination statements. AND elimination 0, you took only a single thing. And what was that thing? So AND elimination took one thing. What was that thing?
It took the first factor or the second
Well,
factor.
no, what was V? You actually
Oh,
put something inside an
it's
AND
a
elimination.
that means we need the or statement, right?
Oh, well, in the AND case, you needed a proof of T and W, right?
Yeah.
So in the OR statement, the first thing that you need to do to use an elimination is what?
Is a proof of T or W.
Yes. And then the other two things are?
A proof of T implies B and a proof of W implies B.
Yes, exactly. So OR elimination is a structure that uses three things. So in context gamma, let's say you have a proof term OR elimination. And I'm going to call my things, let's say D, F, and G. So this has type V, provided that what? So what three things do I need to check?
D is of type T or W.
Yes.
F is of type T implies V, and G is of type W implies V.
Good. Perfect. Whoops. V. W implies V. There we are. And so this is the OR elimination rule. There's only a single one. So AND had one introduction rule, but two elimination rules. OR has two introduction rules, but one elimination rule. Now, this rule is tricky. This is the hardest of the proof rules. Any questions about that? With an AND statement, you just directly squeeze one of the things out of it. But with an OR statement, you sort of can't squeeze a thing of a given type out of it, because it might be something of type T or something of type W. Well, you want to actually produce something. Like, that's not of type T or W. You want to somehow reduce that. So with an AND statement, you had T and W. And then from that, you could produce something of type T. That was one eliminator. Or you could produce something of type W. That was another eliminator. But here you have T or W. You can't produce something of type T out of it, right? So in other words, if you're given Microsoft Excel, you can't produce an incel, or vice versa. But you can conclude that that thing is going to mistakenly assume that something is a date. That's something in common. That's the intersection of the Venn diagram. In fact, implication in classical logic wasn't denoted with an implication arrow. Rather, it was denoted by, well, the thing being implied should be a subset of. So implication was denoted by this symbol. So if this thing is in the intersection of both of these things, then that implication is this thing is a bigger, the universe of things satisfying this criterion is a bigger universe. Oh, sorry. That's okay. Okay, this example does not work. Never mind. The Venn diagram says that this is a subset of this. It would have to be the other way around. Okay, never mind. That example does not work for intuition. And it's actually the other way around. This makes it look like this implies this. So that works, except for this is sort of the universe of properties that this satisfies. So every point is a property satisfied by something in this set. So this shouldn't be, there's a difference between Venn diagrams and Euler diagrams. This is an Euler diagram, actually. And then containment is opposites. So in fact, implication was actually not this, implication would be this. So for example, all men are mortal. So this isn't a Venn diagram, this is an Euler diagram. Okay, that was a complete digression, but actually an interesting one. Yeah, so when you see these things on Facebook, they're not Venn diagrams, they're Euler diagrams. And then containment is reversed in some way. Okay, anyway, back to this. So you need some common thing to get. You can't get T from it. You can't necessarily get W from it. But you can get some third thing if you have ways to go from each one to the other. So that's why the OR elimination statement has to be the way that it is. Any questions?
So it means otherwise you wouldn't have enough information? Because with
Well,
the AND, we use the analogy of taking two proofs out of a box.
right,
But with the
so if
OR,
you're given an AND statement, then you're always able to get something of type A out of an AND statement, right?
Right, but with the
But you're not
OR,
always able to get something of type T from an OR statement. You might be given the other thing, right?
right, because you don't know what is the other thing.
So if you want to use an OR statement, well, you need to get some logical statement from it, right? From an AND statement, we could always get a proof of the first thing, and we can always get a proof of the second thing. For an OR statement, though, you can't do that. So if you want to get a proof out of an OR statement, you need to prove a third completely unrelated thing. but you need to also have implications in both directions. So you need to show that if you knew T, then you could conclude something. And if you knew W, then you conclude the same thing. Right?
Yes.
So in programming languages worlds, if we thought about Racket, for example, in Racket, we were allowed to write statements like if true, then 0, and here I'm going to put maybe the empty list, right? So here, this is an if statement, but the results depends on the condition. So this is a number and this is a list, and they're of different types. So for example, if you had a Boolean here, a Boolean is either true or false, right? So depending on what value the Boolean has, you're either going to get 0 or a list. Well, that's not allowed in logic. In logic, so this statement has type neither. Might be a bool or might be a number. In logic, if you want to use the statement, you have to produce something of a common type. Not allowed in logic. So in other words, in logic, you'd have to write if you have some Boolean, then it could either be, let's say, 0 or 17. Those are both numbers, whereas here you have a number and here you have a list. If you want to use a Boolean, you need to produce something in the true case, you need to produce something in the false case, and both of them have to have the same type. That's a programming languaging analogy that shows in one way in which this is different from Racket. Other programming languages will enforce that constraint. So other programming languages, if you write a bool statement, the true and the false cases have to produce something of the same type, or it'll throw a type checking error and won't let you compile the program. Okay, that's a digression. Okay, let's make these rules now into bidirectional rules. So first off, if I synthesize the type of, if I do a synthesis here, would I be able to conclude a synthesis downstairs? Actually, yes, that seems to be the case. Oh, right. Yeah, exactly. So if I do a synthesis here, I've been speaking for too long. That should have been a very obvious answer. Let's say I'm able to synthesize. What type should I synthesize from this? What type could or intro T be if T has type T? What is W, for example? If T has type T, then or intro 0T has type T or W for any W, right? Does everyone see that?
Could you repeat the statements just to be sure?
Let's say that T has type T.
Okay.
Or intro 0T has type what then? What type
That's-
can it have?
Well, it can have T or W. Wait, just
And what is
what?
W in this case?
I don't think we established that.
Anything, right?
Yeah,
You can put any type there and it would satisfy it.
because we haven't established it, so we don't really have a definition to work with.
Right. So if you're able to synthesize the type of T, that's not useless. You can't synthesize the type of W, right? You're not able to synthesize the type of this term, rather. So we won't have synthesis rules. We'll have checking rules.
Oh, okay.
And
Yeah.
so if I'm able to type check T as T, then what am I able to do here?
Then you know that since T is type checking to little t, then T or W could type check to T.
Yes. Well, rather, if we know this, we can conclude this. So in order to type check an or intro term as T or W, you type check the thing inside of the term as T, right?
Yes.
And then similarly for W, for this rule here.
And then also,
Now, what about this rule? Can the rule at the bottom operate in type checking mode? Or rather, are we able to type check everything? Can we put type checking everywhere? So let's say I'm trying to type check this, right?
yes.
Then what do I do here? Can I type check D against T or W?
Yes, you could.
What are T and W?
We didn't really establish that.
So algorithmically, what we should do here is what?
I mean, I guess we could try seeing the
Equivalent or congruent?
No.
And, okay, got it.
D is some term. We need to know that D has type T or W. We have to synthesize this, right? Because we don't know what T and W are. So we should
Right.
operate in synthesis mode here.
Okay. So that just
Then
checks it.
if we're given V, then also we already know what T is. We've gotten it from here. And we know what V is. We've gotten it from here. So here, are we allowed to do a synthesis? Sorry, are we allowed to do a checking? Or do we have enough information to just do a type checking?
Well, yeah, if we established it with
Yes.
V. But we have it. Oh, yeah, we also did W and V as well. So checking.
Yes, D synthesized T and W. And then at the bottom, we're trying to type check against type V. Now, by the way, you can imagine a rule in which you're doing synthesis here and doing synthesis here. But we're not going to consider that rule.
Okay.
We won't consider the synthesis rule.
Also, question.
Yes.
So for the on the upper line of O or E and the second and third terms, you said that we already know V, but isn't V known from the line below? So it doesn't really.
That's what I mean.
Already being known.
Because algorithmically, if you know what V is right here, then after you synthesize this, you can pose this problem. You're allowed to do checking mode.
Okay. Okay, yeah, because if that's the conclusion we want, then I guess it's sort of like we assume something and then we just work with that.
Now,
So-
on the other hand, if you were able to synthesize both of these, or even if you were able to synthesize one of them, for example, then you'd be able to, then you would know V, and then you would get synthesis here.
Sorry, I can't see your cursor. Oh, yeah, okay.
But we're not going to have that rule in our system. We're just going to
Oh, yeah.
have the rule in red.
Yeah, I got it.
So there are only 3 rules. For or elimination statements, we're always going to do checking mode, not synthesis mode. And then for the other two, they only operate in checking mode. And it doesn't make sense to do these rules in synthesis mode. So forget the rule in green. These are our rules. You'll have to add these 3 rules to Proust in the second assignment. So in the second assignment, you're going to need to add 3 new proof term structures, 1 new type structure. And then after you have those, you're going to have to add these 3 rules. 2 rules, actually all 3 rules would be added to the type checking function. You're not adding any rules to type synthesis in this assignment. Okay, now I hope to also do knots today, but I don't have time for that, but I do have time to do some examples. So let's do some examples. Oh, by the way, does anyone have questions about these rules? Or actually, have I gotten Venn diagrams and Euler diagrams backwards? Is this in fact a Venn diagram? I need to look up what a Venn diagram and what an Euler diagram is. Interesting. No, oh, so this might actually be a Venn diagram. So Venn diagrams don't represent intersections of things. They represent properties which are at the intersection of things. Or Venn. That's so homework, look up the difference between Euler and Venn diagrams, because this only makes sense as one of them. Okay, let's go to here. I think it might actually be a Venn diagram. So what are my 2 examples? Let's do, here's the first one. A implies A or B. How do I prove that? Martine, how do I prove this? What the statement is, if I have a proof of A, then I have a proof of A or B, right? How do I handle the if? Okay, anyone? What do I start with?
With lambda A.
Yes. Now, A is going to be bound to a proof of A, and how do I prove A or B?
We use or intro 0 A.
Yes. On what? What do I put here?
On little a.
Yes. So I prove A or B by saying I'm handing you a proof of the first thing in the or statements, and here's my proof, it's little a. So this term has type A or B. A implies, sorry. Okay, this has, I've spoken for way too long today. Okay, 1 more example or 2 more examples? 2 more examples. Let's do A or A implies A. What do I do? Okay, how do I start the proof term? Well, okay, I'm assuming A or A. Let's call that assumption D. And then what? How do I use that assumption?
We need or elimination.
Yes. What's going to be the first thing that I feed the OR elimination statements?
That'll be D.
Right. Now, the other two things, what are the types of the other two things that I need to feed into the statements?
A is a proof. A implies A and A implies A.
Yes. So I need a proof that I need these two proofs. How do I give a proof of A implies A?
That will be lambda A.
Yep. And how do I give a proof of A implies A again?
It's the same thing. Lambda A.
So here are two proofs of A implies A. My OR elimination structure always needs three things. It needs a proof of an OR statement, and it needs two ways to use it. So this right here, that term has type A or A implies A. And as the final example, let's do A or B implies B or A. Okay, what do I do?
Lambda D.
Now, what am I going to return? Oh, rather, okay, no. Okay, so what do I do next? You tell me.
It's like the same thing where we reverse the AND statement. We need to do OR elimination.
Yep.
Right?
But in the AND case, we started with an AND introduction.
Yeah, because we have to construct a new box essentially. But this time
Yes.
we are doing something different.
OR elimination, sure, we're
no.
using it on D. And then what do I need to provide? I need to provide two proofs. What are the proofs of?
It's A implies B and B implies A.
Nope, that's not the proofs that we want to provide. Those are not the types. We'd like to show that A implies what? What are we trying to show? We're trying to show B or A.
That A implies B or A, and B
Yes.
implies B or A.
Exactly. So how do I prove A implies B or A? What's the proof of that?
Is it OR introduction?
No, it's not. An OR introduction does not prove an implication.
We need
You're trying to
lambda.
prove.
Oh, sorry, abstraction, lambda.
Yes. So what are you taking? You're taking a proof of A, right? So let's call that lambda A. Okay, now what?
Now use OR introduction to get
Yes. Which one am I using?
introduction 1.
Yes, because I have a proof of A, and that's the second factor of what I'm trying to prove. Okay, so that proves A implies B or A. Now, how do I do the other proof?
It's going to be lambda B.
Yep. And
then OR intro 0 on B.
Yep. So, okay, now I'm running out of space to close brackets. So that closes the lambda, and then I need another bracket to close the OR elimination statements. And that's the proof. And if you think about it as I'm packaging things, you can also make helpful analogies like the walnut analogies, but it's a very tactile proof. You're giving a program, you're saying how to do this. It's very nice, and you can make pictures of it. So hopefully today's class should have, well, I taught you about and or, but this should also have clarified something about proving implications as well, right? Now you can see implications as also actions and programs and commands on how to do things. The walnut vending machine analogy. right? You're abstracting a process for how you would get food in those conditions. What you're providing with is the program for how to do this. And similarly, this is how you write programs when it comes to logical constructs of and or. This is how you program in logic. Here you've written some logic programs. Any questions? Was that cool?
Yeah.
Okay, well, we're going to do a postmortem of the midterm next class. And I think that's all for today. Yeah, by the end, I had already somewhat exhausted all my energy. So the end was less organized, but that's, I can only speak for so long after managing a midterm over the weekend. Yay, we finally got through the midterm. That was also a load of work for me to ensure that everything was properly configured and catch up with a bunch of things. But right, and I'm going to shortly upload the programming and proof assignments. So you can already start working on the programming assignments, although I'll send resources about how to go with match. And the programming assignments, when they're uploaded, will also have the proof rules written in them. So just as a reminder, you're supposed to add structures that handle these, and then you're supposed to add cases to, and this will also be written in the assignment. The pretty parsing, pretty printing, and pretty printing functions. And then for each rule, you're going to have to either add a case to the type synthesis or the type checking rules. And that's how you extend Proust to handle other logical connectives. And then after you extend it to handle that connective, you can use it to prove homework problems that use and ors. And each subsequent assignment will use the ones that came before it. So the statements for or will use those for and. And then and or, the implementation ones are separate. Okay, so hopefully that was enjoyable. See you tomorrow. Bye.
See ya.
Thank you.
No worries.